Hello everyone, welcome to Samadhan Life Science. In today's video, we will discuss about one important thermodynamic property in electrochemistry, the relationship between standard electrode potential and Gibbs free energy. So before going to the equation, let's understand the standard electrode potential. This is a measure of the tendency of a chemical species to undergo reduction or to gain electrons. And this is measured under standard conditions, for example 1 molar concentration for aqueous species, 1 atmospheric pressure for gases, and at 298 Kelvin temperature. And the important thing to remember is that if you have a positive value of this E naught, then the chemical species is likely to undergo reduction, or we can call it a oxidizing agent. And if you have a more negative E naught value, then it is less likely to undergo reduction and easy to oxidize. Now, in a standard electrochemical cell, we have two half cells, cathode and anode. Reduction happens at cathode and oxidation in anode. And to get this cell potential, we have to do reduction potential of cathode minus reduction potential of anode. And overall, if this cell potential value is positive, then we can say the process is spontaneous. Okay. Now in a electrochemical cell, chemical energy is converted into electrical energy, and maximum useful electrical work we can get from that process we can write as W max is equal to nFE cell. Now this N is the number of electron transferred in the process, F is Faraday constant, E cell is the standard cell potential which tells us about the ability of the cell to produce electrical energy. Now this work is quantitatively positive because this is work done by the system, and from energy conversion we can say that the work done by the system will be equal to the change of Gibbs free energy in the process. So we can write delta G is equal to minus W, and so we get this equation delta G naught is equal to minus nFE cell, and delta G naught is standard Gibbs free energy. So if you have a positive value of this E cell, then you get that delta G naught is equal to negative, which means the process is spontaneous. If this cell potential is negative, then delta G naught is positive, which means the process is non-spontaneous. And for zero cell potential, delta G naught is 0. That means the system is in equilibrium. Right. Now let's do some numerical problems. So in this question, standard potential for two systems are given. So the first system we have Fe3 plus 3 electron to form Fe. E naught values are given, and we already have the equation delta G is equal to minus NF E naught. So we can calculate delta G naught is equal to minus N is 3 number of electron transferred here into F into minus 0.04 volt from here, right? So minus positive 0.12 into F. Number 2 system we have here is Fe3 plus single electron to form Fe2 plus. So delta G2 will be minus N is 1. So F into plus 0.76 volt. So this will be minus 0.76 into F. Now we have to calculate the E naught for this third system. Fe2 plus 2 electron to form Fe, right? So for if now see that if we do this reaction 1 minus this reaction 2, then we get this reaction 3, because Fe2 plus comes to this side, Fe3 plus cancel out, and 3 minus 1 electron 2 electron. But we cannot do this simple subtraction for the cell potential values, because this is an intensive property and we cannot do simple multiplication by stoichiometric coefficient here, but we can do this subtraction for the Gibbs free energy values. So delta G3 for this third system will be delta G1 minus delta G2, which means plus 0.12 into F minus 0.76 into F. So this will come around plus 0.88 into F. We have to calculate the cell potential. So E naught for this third system will be minus delta G3 divided by N into F. Delta G3 we have 0.88 into F. N here is 2, so 2F, and we have this negative sign. So F cancelled out, minus 0.44 and volt, right? E naught unit of cell potential is volt. So answer is 0.44 volt. Okay. Now for the last problem for today, the standard electrode potential for two half cells are given here, number 1, number 2, and the standard gives free energy for dissolution of silver chloride we have to calculate. So dissolution of silver chloride is AgCl solid to Ag plus in aqueous plus Cl minus in aqueous, right? Now the first system, for the first and second system we have the E naught values. So let's calculate the Gibbs free energy. So minus, both for both of the system N is 1, so minus here 0.22 into F, and delta G2 is minus 0.80 into F. We have to calculate delta G3 naught. Again, if we do reaction 1 minus reaction 2, then Ag solids get cancelled out and AgCl to Ag plus aqueous and Cl minus aqueous we get. So delta G3 is equal to delta G1 minus delta G2. So minus 0.22 F minus 0.80 F, and then we get plus 0.58 into F. Now F value we have here. So this 0.58 was in volt because this is the potential difference, into we get this Faraday 96500. The unit is coulomb mole inverse. So by multiplying volt into coulomb we get joule, and the value will be around this, but the unit for the Gibbs free energy will be joule, because coulomb into volt is equal to joule. Okay, so be notice the unit, and be cautious for the unit in your exam too. So I hope you understood the concept and can apply this in your exam for the numerical problems. Thank you for watching. See you in the next video. Bye bye.